All right, hello. Today our reading is on lesson 4, what is magnetism? And this goes with our magnetism experiments that you have done in class or will be doing in class. And it starts off with, again, an exploration that you can, do at home if you like, if you have the materials, but it should go with what we did in class. But I'm going to start on page 411. Magnetism. Does the door of your refrigerator look like a scrapbook and message center? Papers, photos, notes, and reminders may be held in place by many colorful refrigerator magnets. I know my refrigerator is like that. We have, lots of little things that my sons have done, or a calendar to remember when things are. And it's all up there because of magnets. Magnets attract the magnetic materials such as steel, found in many refrigerators and paper clips. This attraction is what makes the magnets cling to the refrigerator and to paper clips. As you may know, all magnets have the property of magnetism. Magnetism is a force that acts on moving electric charges and magnetic materials. So how do magnets support a heavy maglev train? Electric current produces enough magnetic force to lift the entire train. The pushing and pulling forces between the magnets also move the train along the track. And so if you look at the picture there's a caption, I'll read the caption. It says, magnetic forces lift and move this maglev train as it speeds along about 1 centimeter above the track. So the train is actually not even touching the track. It's levitated, it's lifted up because of the magnets that are pushing away from each other. That also causes it to move very, very quickly and make it a very, very smooth ride. Okay, so name two objects that are attracted to magnets. Well, think of things that have steel inside. Okay, and they gave you a couple examples up there, but maybe you come up with some other ones that you know of that aren't in the chapter. And then number two, how do you use magnets in your daily life? Well, they gave some examples up here, but what are some other ways you can use magnets? So put that on your post-it note. And we'll move on to 412 when you're ready. Magnetic fields. All right, so this section is about magnetic fields. Each magnet has a magnetic field around it. A magnetic field is a space around a magnet in which magnetic forces operate. The magnetic field extends out in all directions from the magnet. The exact shape of the field depends on the shape of the magnet. And so if you look at the images to the right, it says iron filings near a bar magnet show the magnetic field is strongest near the poles. So the poles are the very ends of the magnets. And so if you see here, this is where you kind of have the most material kind of right here bunched up on the end. Okay, and notice it's almost, kind of circular here. It spreads out in all directions. All right. Okay. All right, let's talk about those magnetic poles, the ends. The two ends of a magnet are called the magnetic poles. The end of a magnet labeled north is pulled to the geographic north by Earth's magnetic field. So the Earth has a magnetic field. Then labeled south is pulled to the geographic south by Earth's magnetic field. The magnetic field is strongest at the magnet's poles and gets weaker away from the poles. The north pole of the magnet attracts the south pole of another magnet. The north pole repels the north pole of another magnet. So what they're saying here is similar opposites attract and similars repel. Similarly, the south pole of a magnet attracts the north pole of another magnet, and the south pole repels another south pole. Okay, and so if we look at our images, our second one, it says a horseshoe magnet has a magnetic field that looks like a large U shape, so it gives you a different type of magnetic field. And then if we look at the last image, opposite poles attract, like poles repel. And so if we see the north and the south poles that are together, they're trying to touch each other, trying to come together. Okay. And so if I look at question number 3, it says, how are magnet fields of the bar and horseshoe magnet alike? Well, look at the two images. What do you see that's the same in both of them? Okay. And then number 4 on your post-it note, draw two bar magnets in a position so that the magnets are repelling each other. Label each end of the magnet with an N for north and S for south. So how would you draw the magnets so they're repelling, which means they want to stay away from each other? Okay, how would you draw it? And let's go to page 413 when you have your post notes. Magnetic compasses. A compass is a helpful, easy to carry tool. Wherever you are on Earth, one end of the compass needle will point approximately to Earth's geographic north pole. It follows an imaginary line that connects the magnetic pole of Earth. Once you know which direction is north, you can easily determine south, west, and east. So your compass is always going to point north, and so if you know which way your arrow is pointing, then you can figure out your other cardinal directions. For a compass to work properly, its needle must be lightweight and it must turn easily. The compass cannot be close to a magnet. Otherwise, the needle will respond to the pull of the magnet rather than the Earth's magnetic field. Right? So if you have a magnet in there, it's going to mess up your needle and it's not going to really tell you which way north is. So you have to be careful. All right? And if you look at that lightning lab section, we call this a sidebar, a little extra information, and it kind of gives you a different experiment that you could try to create your own compass at home. All right? And if I look at question number 5, why does one end of the compass needle point north? All right, so I kind of search and sign back through what causes the compass needle to point north. And as I'm looking, it says, once you know which direction is north, it says, let's see, wherever you are on Earth, one end of the compass needle will point approximately to the Earth's geographic north. It follows the imaginary line that connects the magnetic poles. Okay, so it's kind of pulling towards that magnet, or pulling towards that pole. And let's look at question 6 and 7. If you find a metal bar, how can you determine if it's a magnet? Well, what kind of tests could I do to check if the metal bar is magnetic? What is something I could do? And then number 7, how is the Earth like a magnet? Okay, think about the poles and think about how compasses work to kind of help you answer that one. And so put that on your post-it note. And always, if you have any questions or you're not sure, put that on a post-it note because you can discuss with your teacher in class tomorrow. That's our reading for lesson 4.